Okay, hello, welcome back everyone. And today we're going to be continuing, I'm going to be continuing my set of multiple choice questions from the AP Calculus B final. And we're going to start with question 23, which looks to be a logistic equation. Yeah, logistic differential equation. All right, so a population of wild mustangs in New Mexico desert is represented by the logistic differential equation dp dt equals 0.08p minus 0.0004p squared, which thankfully they factor for us into this 0.00004p multiplied by the quantity of 2000 minus p. So letter A is what is the carrying capacity for the population. So if we remember, the logistic equation is P equals Kp multiplied by M minus P, where M right over here is the carrying capacity. So if we just start lining up our numbers here, we can have the 0.0004. That lines up very nicely with the K over here. And 2000 right over here, that lines up really nicely with M. So it seems as though the carrying capacity is 2000. Okay, so we have the carrying capacity is 2000 horses. Now we know that the initial population, P0, is equal to 10 horses. Find the formula for the population in terms of T. So the part that we're supposed to have memorized for this question is that if we know dp dt is equal to kpm minus p, then we automatically know that p is equal to m over 1 plus a e to the negative mkt. That is just one of those general solutions which you should have memorized. Is for the logistic equation and how it links together with the logistic differential equation. So let's go ahead and copy that population equation. We can start substituting things. The first thing to substitute is we know that M is 2000. So we'll put that right there. And if M is 2000 and K is 0.004, then negative MK, now here's a little bit of a trick. You can actually find it in this differential equation. It's right there. It's negative 0.08. If you're unsure about that, make sure that you just multiply those numbers, and you should get 0.08 in this case. Now, as far as the A is concerned, A is not the initial amount. It's not going to be equal to 10, but it is going to be related to 10. And the correct way to solve for A is to use this initial condition, P0 equals 10. So we're going to go ahead and write out our population equation as it currently is. We'll substitute P0 is 10, and then we'll simplify that. Of course, up over here we have negative 0.08 multiplied by 0. That's just 0. And even better, e to the 0 power, that's just 1. And then a times 1 is just equal to a. And now we've got an equation which we can solve pretty easily. 10 is equal to 2000 over 1 plus a. All right, let's multiply both sides by 1 plus a. That's going to cancel out our denominator on the right side. And now this is just an Algebra 1 problem. And so A is 199. Like I said, the A is related to the initial condition, but it's not actually equal to the initial condition. And with our A, we'll just substitute that into our population formula. And that does it for part B. Part C, Oh, there is no part C. Number 24. We have the function Vt equals 12t squared minus 4t. That's the velocity in meters per second of a particle moving along the x-axis where t is measured in seconds. Use analytical methods to find the particle's displacement from 0 to 2. Now I'm looking at this question and I'm seeing displacement. We remember that there's actually an equation for displacement that we learned a while ago. The displacement is just the integral of the velocity. And to bring it back to the fundamental theorem, it's equal to the position at B minus the position at A, which is the change in position. So this gives us a couple of different ways of finding the displacement. We can either find the displacement using the velocity, or we could find the displacement using position. Either one of those will work. Now, as it happens, we don't need to know the position because we have the velocity function, and we also have A and B is 0 and 2. So the velocity function is 12t squared minus 4t. A is 0, and B is 2. We can use our methods of antiderivatives. So antiderivative of 12t squared is 12 multiplied by the antiderivative of t squared, which is 1/3 t cubed, minus 4 multiplied by the antiderivative of t, which is 1/2 t squared. We're going to take this equation and we're going to evaluate it from 0 to 2. Now, it's probably a good idea to simplify this a little bit. So 1/3 of 12 is 4. Half of 4 is 2. And we can clean that up just a little bit. And now we'll just substitute our upper limit minus substitute our lower limit. Okay, 2 cubed is 8. Two squared is 4. 0 cubed is 0. And 0 squared is also 0. We'll do some multiplication now. Some subtraction. And we'll finish that off with more subtraction, leaving us with 24. For units, I notice in the question that the velocity is in meters per second and t is measured in seconds. So that tells me that since the seconds are going to cancel out, the displacement will have units in meters. That's our 24. Let's take a look at our 25. The function Vt equals t squared minus 4 is the velocity of a particle moving along the x-axis where t is measured in seconds. And the velocity is measured in meters per second. Determine when the particle is moving left, right, and stopped. So this is actually a pretty long question. There's a lot to it. So the first thing to figure out is when during my interval is the particle stopped. When is the velocity equals 0? Okay. So that's what we're going to do. We're going to take our velocity equation and make that equal to 0. And that's not a difficult solve. We get -2 and 2 for t. But of course, we're also told that t is greater than equal to 0. So -2 is not going to actually work for us. So we're left with the one place where the particle changes position. Everything to the left of 2 has to be for t less than 2, the particle is going to be moving in one direction, and in t greater than 2, the particle is going to be moving in another direction, or maybe even the same direction. In any case, the only way that the particle could change direction is if it stops first. So now we're going to take a look at our number line. Now, the lower part here, that's going to be our values of t, and above the number line, that's going to be our velocity, or v prime of t. So we need to know, is v prime positive or negative? If v prime is positive, the particle is going to move to the right, and if v prime is negative, the particle is going to move to the left. So from 0 to 1, we're going to pick a point, and I think the point's going to be 1. If v of t is t squared minus 4, well, then we need to figure out the velocity at 1. And the velocity is 1 squared minus 4. I'm not interested in the actual number. I'm just interested that the velocity is actually negative. I think earlier I said something about the v prime. Yeah, I see v prime over here. And actually, you don't need v prime. You just need to know the velocity. You would need to know x prime, which is the velocity. So here I have marked that from 0 to 2, the velocity is negative. Let's check at a number greater than 2. Conventional wisdom says you can use 3, but if you know me, you know I like to use a bigger number than 3 just to make the calculation easy. Let's pick 100. Remember, it doesn't really matter what the answer is. We just need to know if it's positive or negative. So with a really big number, it's really easy to tell that this is going to be a positive velocity. Okay. That completes our number line. Now we can do some analysis here. We know that for t between 0 and 2, the particle moves to the left because the velocity is negative. And then for t greater than 2, the particle is going to move to the right because the velocity is positive. And then the particle is stopped at t equals 2 because the velocity at 2 is equal to 0. So remember that between these critical numbers, these places where the velocity, or x prime, is equal to 0, the velocity has to be the same. So everything between 0 and 2 has to have the same velocity. Everything from 2 to infinity has to have the same velocity. Let's take a look at letter B. Find the particle's displacement for 0 less than t less than 5. Now, it doesn't matter that these are less than or equal to or not, because we are going to integrate here in this case, and our velocity is also continuous from 0 to 5. Now, I think I wrote up here the displacement formula. Yes, I did. So I'm just going to copy that and put it back down over here, because it is the same displacement. Velocity is the integral of velocity is displacement, and the displacement is equal to the position at B minus the position at A. Well, we don't need the position of B minus position of A, since we don't have the position formula. We know that velocity is, what is that, t squared minus 4. And we know that A and B are 0 to 5, which sets us up nicely for the integral. So let's take our antiderivatives. Antiderivative of t squared is 1/3 t cubed, minus the antiderivative of 4, which is 4t. And then we're going to evaluate that from 0 to 5. Take our antiderivative, substitute 5, and then we're going to minus our antiderivative, substitute 0. We're going to do some evaluating here. So let's see. 5 cubed is 125. 0 cubed is 0. Then we'll do our multiplication. Then we'll do some subtraction. And then finish it off with the last subtraction. Units are again meters. Great. Let's take a look at part C now. And C is find the total distance traveled for the particle from 0 to 5. Now you have a couple of things in your advantage for doing this, and the first one is that you know that the particle is going to change direction at t equals 2. You also know that the particle is moving to the left from 0 to 2 and to the right from 2 to infinity, or in our case from 2 to 5. Now, if the velocity is negative from 0 to 2, if we integrate the velocity from 0 to 2, that's going to give me a negative number. Or if we come back down over here, this should give me a negative number. In fact, why don't we just go ahead and do that right now? Okay, so like predicted, we get a negative 16/3. The next interval that we're going to do is from 2 to 5. Antiderivatives next. Then we substitute. Then we evaluate. And then finally, we're going to take these two displacements and we're going to add them together. We're going to add the absolute value of each of them, and that's going to give us our total distance traveled. And again, this is going to be in meters. So that's going to do it for 25. And let's take a look at 26. We need the region bound by the graph of x cubed minus 6x squared plus 8x and y equals 0. So your first task here is going to be to graph this. I'm taking a look at this polynomial and I see that this is the lead power is cube and the lead coefficient is positive. So that means the shape of this must be similar to this curve right here, up, down, up. Positive cubic pattern. That's something that you should have memorized, how that lead term affects the shape of a polynomial. This means that I also have a maximum of 3 roots, which we should get from the fundamental theorem of algebra, actually. And I think this is factorable, so why don't we try and factor that so we can find out all 3 roots. So first we could definitely factor out that x. Then we could factor to x minus 4, x minus 2. And that gives us my 3 roots. My 3 roots are going to be at 0, positive 2, and positive 4. So graphing this, what do we say? We have a root at 0, we have a root at 2, and we have a root at 4. So 0, 2, and 4. Again, we know the pattern here. We know it has to be increasing from the left, decreasing, and then increasing to the right. So that tells me I have 2 regions here. This region here on the left is from 0 to 2, and this region on the right is from 2 to 4. Furthermore, I know that this region from 0 to 2 is going to have a positive integral, and then the region from 2 to 4 is going to have a negative integral. So I'm going to evaluate those 2 areas separately. So let's get back to our problem. So area 1 is going to be the integral from 0 to 2 of x cubed minus 6x squared plus 8x. So we're going to go with our antiderivatives first. Antiderivative of x cubed is 1/4 x to the 4th power. Antiderivative of 6x squared is 2x cubed, and then the antiderivative of 8x is 4x squared. So I have my antiderivatives. I'll substitute my upper and lower limits. So substituting my 2 first, well, I'm not going to do a whole lot here. I'll just put the 2's in. And then for substituting 0, well, since each one of these addends in the antiderivative have an x, that when I substitute 0, I am just going to get 0. So saving just a little bit of time here, let's evaluate our antiderivative at 2. And of course, this is going to evaluate to 4 minus 16 plus 16, or just 4. Okay, now that we have the area 1, we got to get area 2. This time we already know our antiderivative, so things should be a little bit easier. So again, this time we're going to evaluate our antiderivative from 4 to 2, and we're going to subtract them. We're expecting this antiderivative to, or we're expecting this integral to evaluate to be a negative result. So we'll substitute 4 and 2 into our antiderivatives, and then we'll evaluate. We'll do the exponents first. Now we'll do all the multiplication. Then we'll do some subtraction. And finally, subtract 0 minus 4. And like we expected, this second integral evaluated to be a negative 4. So if I want to find the area of the region bounded by this cubic and y equals 0, then I have to add the absolute value of these two areas. Area 1 was 4, and area 2 is also 4. Remember, the integral was negative 4, but the area is 4. And to nobody's surprise, we get an area of 8. And that is going to do it for this video. We'll see you next time for more of the AP Calculus review. And have a good one, everyone.